love polar. We should be doing so much more graphing in polar. If you really want some good stuff, really good stuff, look at how to multiply complex numbers with polar. Oh my gosh, it's like mind-blowing. I'm not kidding. I'm really not kidding. Look it up. It's amazing. Especially if you can find something that really expresses the full circular nature. Anyway, anytime we draw curvy things, it seems like polar just goes so much more naturally. Cartesian, you've got these rectangular grids. And how does that work so well when you're doing curvy, beautiful graphs? Polar is amazing. We should do more of it. But here we go. Now, when you are looking at a plane, you can either put on it the XY coordinate system, or you can put on it the polar two-dimensional system. And you already know that in the Cartesian world, Pen, you better turn on, or thank you. Okay. In the polar world, we have x comma y, x the horizontal, y the vertical. We're familiar with that. Realize that the polar point is r comma theta, where r is the distance that point has to the pole or / origin. Now the AP test seems to just call it the origin, but in polar words it is the pole. The polar axis is the positive x-axis, because that is where you are at 0 radians, and we will only deal with radians in this class. And the positive direction of theta is counterclockwise. So when I plot a polar point, I have actually not a distance, a displacement from the origin, I'll explain in a moment, and an angle of rotation. The thing is, r can be positive and negative, theta can be positive and negative. So what you want to understand is that you're used to a very stable x-axis, y-axis. They are horizontal and vertical. You want to imagine that the polar axis is going to take a line, and I'm not going to draw it horizontal or vertical. Here's 0. A line has a positive side and a negative side. However, if you rotate that line 360 degrees and think about it, can you see plus and minus kind of changing circumstances on you? Because once I go from 0 radians, when I'm at 0 radians, I'm really looking at the x-axis, and a positive r is going to be over on this side, but a negative r is going to be over where you are used to being at angle pi. Then as it begins to rotate, it's rotating based on theta. Theta causes the line to turn. And as it is turning, r is simply going, where am I? I'm here, then I'm going to move, and then I'm going to go back, and then I'm going to go negative, and then I'm going to come back, and I'm going to go to 0, and then I'm going to be positive while turning. So if any of you went to the Science Center in Balboa Park when you were kids, do you remember when they had that sand wheel where you had a brush? I spent the time they're trying to create polar graphs and found how difficult it was to create polar graphs by hand. Because I just simply can't move the way that a sine wave moves. But the idea is that it's moving back and forth while turning, and that is creating a curvy graph. And it's beautiful and amazing, and oh my goodness. But you have to realize that while it is turning, positive and negative sides are kind of swapping some bits. So when my angle is at pi, I want to really make sure this is clear to you. When I am at angle pi, I have rotated that much, and at that time, this is the positive axis and this is the negative axis. If I have a negative radius when I am located at pi, say it's -4, this is the polar point where r is -4 and theta is pi. That is also the point r for angle theta, or angle theta, angle 0. Every point on the xy plane in rectangular Cartesian world, there's only one ordered pair. Polar world, infinite ordered pairs to get you there. Now, don't look at that yet. Haha. Realize that if theta is negative, then you are starting at the positive x-axis and you are turning clockwise. Be aware that on the AP exam, they will sometimes ask you, I need to look at the exact words, but how your graph is moving. They will ask that to you in some sort of bunch of words. Sorry. Often what they are wanting you to determine is whether you are moving toward the origin or away from the origin. But that's if you are specifically looking at the movement of the graph based on dr d theta. While I am turning, how is my r changing? Is my r moving toward the pole? Is my r moving away from the pole? Realize that that depends upon whether you're dealing with a positive r or a negative r, a positive theta or a negative theta. You need to bring all of that into context when you are looking at whether you're moving toward the pole or away from the pole. Because a positive rate of change just means that I am moving along the line in this direction. But as I turn, that direction turns. If dr d theta is negative, then it is moving this direction on that line while it is turning. And so just bring all that into consideration. Also be careful because sometimes they'll ask you questions about dy dx, and you know that that means slope. Sometimes they might ask you about what's dx d theta, and that's just looking at the horizontal motion while theta turns, or dy d theta looking at the vertical motion while theta turns. And if you're looking at horizontal motion, you're looking at distance from the y-axis. If you're looking at vertical motion, you're looking at changing in distance from, what did I just say? From the x-axis while theta turns. So, with that said, this triangle right here is so important, so important. Are you awake? This is hugely important. Hugely, hugely important. This is everything. Okay. That triangle right there, take a good look at it. It's a right triangle. Do you know formulas for right triangles? Yes, you do. When I look at the Cartesian point of x comma y, that's giving me, while I'm in quadrant 1, mind you, this length of that leg and length of that leg for y. R is giving you a hypotenuse length, and then there's a theta. How many formulas can you create out of that triangle? You can create a lot of formulas. So I want you to think about a formula that you can create out of that triangle. Just a formula. That's all we're doing. We're not solving for anything in particular, just what formulas can be created off of that triangle. And online, I've already got one. Oh my gosh, the sophomore again. Hold on. Shh. Hold on. So, yep. The online people couldn't hear you, so yeah, they're seeing some of it too. So, Pythagorean. Oh, sorry. Yes. Yep. And I started saying something. Did you hear what I started saying? So understand that if you know this triangle right here, you can create all those formulas. And I want to warn you that if you are going to go into third semester calculus, multivariable calculus, you are going to have the joy of dealing with polar in a couple of three-dimensional situations. One of them blatantly uses it. The other one kicks off of it. You need to know this triangle because it is going to kick off into some three-dimensional formulas in your next calculus course after this. Now, there are actually only 4 formulas that get mentioned, but do you see that there are more than 4 formulas here that you can use? And that's what I want you to understand, is that you have the power of creating many more formulas than the 4 standard ones. Now, the 4 standard ones are Pythagorean theorem, and then good old SOHCAHTOA. And, whoops, opposite, hello, I can do this. So sine theta is y over r, cosine x over r, tangent y over x. And I want to mention, hey, look at y over x. Have you ever thought about a y over an x before? Slope. Tangent theta and slope are one and the same, because when we look at our rotating line, it's always through the origin. So whatever my xy coordinate is, if I look at it with respect to the origin, that y over x is always the slope of the line that is rotating. What's awesome is, you know where x and y are positive and negative. I realized I just wrote z squared. I was thinking 3 dimensions, wasn't I? That should be r squared. Hello. Maybe some of you are trying to tell me that. I don't know. Yeah, ton of formulas you can get here. I have 6 trig functions, and I also have 6 inverse trig functions. I mean, we can go on and on. Now, one thing I want to point out to you is, if I multiply the r over to the other side with the x and the y, then I wind up with 4 equations where for each equation, one side has Cartesian x's and y's, the other side has r's and thetas for the polar world. And then I'm going to bring up the 4 formula, there they are, the official 4 formulas you're expected to know. But who needs to memorize those when you've got a triangle and literally just know the triangle? Is that going to be a lot less memorization? Far less memorization and far more powerful. However, when you're going quick, you do need to remember that x associates with cosine and y associates with sine. Now, when you are converting one direction or the other, converting from Cartesian / rectangular into polar is super simple. All you're going to do is take that x equals r cosine theta and that y equals r sine theta and literally substitute. Just substitute it in. So like with number 24, if I substitute directly in, then I have r cosine theta plus r sine theta equals 9. Now, what does it mean to be converted? That's converted. If you are simply told to convert from one format to another without an expression, or without being told the format that you have to have that other expression in, as soon as you have no x's and y's and only r's and thetas, you are converted. But if you were asked to isolate r and solve for r in terms of theta, what would you get here? A little bit of algebra play later. So the direction of converting from Cartesian to polar is pretty straightforward, and then play with the algebra until you have whatever you need. Before I forget to say something, I'm going to come back over here because I need to point something out that is truly frustrating. When we are dealing with functions in terms of x and y is always the output where x is the input. Polar, theta is the input. I've got, oh, now what did you do? Okay, I'll put up with it because I don't want to have to go to Chrome. Yeah, we're all school internet. I'm blaming that, but it's also my computer. All right. Very important, look at the ordered pair r theta, look at the ordered pair xy, and understand very clearly that we are used to the first of the ordered pair being input and the second of the ordered pair being the output. That reverses with polar, but you can also think that it's assigned alphabetically. X comes before y in the alphabet, r comes before t in the alphabet because that is theta. So just be aware that the input theta for a polar function is actually written as the second of the ordered pair. The output is come on screen, there we go, is the, yeah, okay, moving on. Now, I'm going to tell you the easiest way that I have found to convert from polar to Cartesian. Are you listening? I personally believe that always the easiest way to convert is to look at your trig functions and just let the triangle do its thing. Don't worry about the R, worry about the trig functions themselves. Now, there are situations where theta may be just by itself and not in a trig function. In that case, you need to bring in an inverse trig function. But let the triangle guide you. Like the Illuminati triangle. Okay, anyway. So, what is tangent when you look back at that triangle? What is tangent of theta? So what I'm going to do is I'm going to write r equals y over x times, and what is secant? Because it's cosine's reciprocal, and that means instead of adjacent over hypotenuse, you got hypotenuse over adjacent. And when you look at the triangle, hypotenuse over adjacent. And then go, oh, interesting. Look at that. Did I put that correctly? Yes. Did I mess that up? Let me double check. Secant. I felt like there was something wrong there. Yeah. Okay, there we go. But now just play with the algebra, see what happens. Seriously, just play with it, see what happens. So maybe you go, hey, that's r equals, let's see, we've got a numerator of y times r, we've got a denominator of x squared. And then do you see anything interesting? What? Oh my goodness. Look at that. Now what equation do you have? Yes. And then you're like, what? That draws a parabola? Wow. Super cool. So again, my advice to you is let the triangle do its thing instead of feeling like you have to impose particular formulas here. And then play with the algebra a little bit. And they're going to give you problems that are designed to either work out nicely or you're just expected to leave an, quote, ugly looking answer. You didn't hear that. It's okay. You're not ugly. None of you are. Okay. Moving on. That's how you deal with conversion. You may have to do that on the AP test. Now, it's very important that you understand graphing and how polar graphs. So I actually added these lines in because I realized I was screwing up really badly with viewing my grid. So I brought this one in because I was just having too much trouble accidentally looking at the wrong places for particular angles. So I'm going to focus on using this grid so that I don't mess up as I'm explaining. Now, if I asked you to draw the graph r equals 2, That means that while the theta turns, R is stuck at 2. Imagine a turning line. Here's 0, and it's rotating about that line. Whee! And you've got a point stuck right there as you go around. Circle it is. Is that what you got? Yay! All caps? Uh-huh. So I get this. Whee! All right. But what if I asked you to sketch the graph r equals -3? Shh, hold on. Let everyone think. Okay, go ahead. There you go. Yeah, so you want to be aware that we never write negative. These numbers, we never write them negative. And we understand that while the angle turns, each of those circles of 1, 2, 3, 4 can at any time represent a positive or a negative R. Just depends on where theta is.
I may be jumping the gun here, but if you were to say, like, taking the integral of that, would you just find the area of the circle, or do you not take the integral like that?
Area coming tomorrow. Yes. It's okay. I know. So r equals -3 is still a circle. If you are drawing from theta to pi, it's actually going to draw this direction, but it's still creating the same shape, the same graph. So that's what you're going to get if you just have r equals a constant. Basic polar graphing. Another issue with basic polar graphing is what if you get theta equals a constant? Then what is that drawing? And don't shout it out. Hold on. So what did I have ready? Let's say theta is pi/3. Shh, hold on. Let everyone have a chance to think. What is that going to graph? And now let me add in that you need to keep in mind that means no matter what r is, up and down that line that is stuck at pi/3. What is it graphing? Yep, a straight line. You got it. Now, there's an understanding, though, that at pi/3 itself, positive r's are graphing along there. And then on the opposite, I'm doing dashes because often we do dashes to try and show that it's a negative side, especially when we've got something rotating. And the negative r's are going to go along that side. So if you look at all your possible r's, it's an entire line. And what is, that's for r equals sorry, I already have it there. Theta equals pi/3. What about theta equals -5 pi/6? Where's that line at? Yep. So what you want to just realize is there's an understood angle 0 at the positive x-axis. So if it says negative, then you're just going this direction for a 5 pi/6 amount, which is going to take you here to 7 pi/6. So that will create a line where positive r's are at 7 pi/6 and negative r's are at pi/6. So you can have, look at this right here. That means this point can be looked at as r being a negative 4 and theta being a negative 5 pi over 6 in quadrant 1. Ha ha! It's also 4 pi over 6. It's also 4 7 pi, or negative 4 7 pi over 6. I mean, oh my goodness. Yeah. So those are basic graphs. If you have just r equals a number, circle centered at the origin. If it's theta equals a number, then you have an entire line. Now, I want to talk to you about how to sketch polar graphs. I'm trying to not show you that part. Okay. Now, you have done polar graphing before. It may have been a while. So I need to at least talk to you about how to go about creating it. Normally, I like spending more time on this, but I'm going to leave you with just knowing how to get it done. And that is, how do you learn a new language? How do you learn a new language? Besides immersing yourself in it? Translating. You translate your known language into the foreign language first. And it takes time to actually get to the point where you're fluent in that other language. Now, you can try the immersion effect. Don't try it when you're older, though. I recommend not trying it when you're older, but maybe when you're younger, you can deal with it. But who knows? Maybe you can do it when you're older and your mind is still just amazingly. I mean, anyway. So what you want to do, and what I recommend you do, is first draw what this is as a Cartesian graph. If this was y equals 1 plus sine x, then it's the graph of sine x shifted up 1 unit. So there you go, graph of sine shifted up 1 unit. You know that goes through a whole cycle in 2 pi. All look familiar? Now, when you first started graphing the xy on the xy plane, you started with plotting points, xy. And you might have gotten a table of data. I want you to see that you have in front of you not a table of data, but a graph of data, and a continuous graph of data, no doubt, that you can plot on the polar. So let me explain, if you don't see it. When I'm at angle 0, my r is 1. When I'm at angle pi over 2, my r is at 2. While my angle goes from 0 to pi over 2, it's going to go from 1 out to 2. And what I want you to try to imagine is this line is turning, and as it turns, that point is moving along that line very smoothly. And what it creates is an outward going spiral. And I cannot do it justice. Oh my goodness, when I tried to draw polar in sand with a brush, it was sad. So notice how you start at 1 and you are moving down the line farther. First you're here, then you are farther down the line, and then you are farther down the line, and so on until you finally reach 2. Then you have the joy of symmetry. If that just happened while you did 0 to pi over 2, what's going to happen when you go pi over 2 to pi? Whee! It's going to do the same exact thing, and I can't do it justice. There it is. Now, that's that much of the graph. Now, once you're at pi, you then are at an R value of 1, and you are shrinking down to an R value of 0. Realize that when R in absolute value shrinks, you have a spiraling in. Do you see the difference? Spiraling out versus spiraling in. When the absolute value of R grows, you spiral out. When the absolute value of R shrinks, you spiral in. So what is spiraling in from 1 to 0 going to look like? So I want you to think about that. Some of you may already know exactly what this looks like. Yes. And then, so realize that while you learn to graph in polar, you're going to find it easier to do a translation from Cartesian to polar. Understanding that what's going on the x-axis is just creating a rotation, and what's going on the y-axis is your R moving back and forth on that turning line. Now, someone mentioned the shape of this graph. Does anyone know the official mathematical name? All right. Let's see. Jackie's almost got the word. Taya? Oh, Dylan beat you. Ha ha. Cardioid. Yeah. Yeah. And then someone else got the ends in iod. Yeah. Oid. Cardioid. Yep. It is named after the word for heart. So it is amazing. If you find out, just look up videos, just type in cardioid, and you'd be surprised what amazing things where this shows up. This shows up in so many random places. It's crazy. But cardioids are very useful, or they appear all over the place naturally. Anyway, now I want to, what am I doing? There we go. R equals cosine 2 theta. If you look at the Cartesian graph, if the input variable is being multiplied by 2, if I'm looking at y equals cosine 2x, you know what cosine looks like, and normally it's 0 to 2 pi. If x is being multiplied by 2, take the parent graph's x values and do the opposite operation, and you will get what happens. So it is squishing it by 2, and so you get a full cosine cycle in 1 pi. And you can draw as many cycles as you want with that graph, but now let's talk about what is that going to create as I draw a polar curve. And I'm going to tell you that, well, you know what? I'm going to go with the way the textbook is drawing it. Should I? No, I'm going to go my way. Haha. So I personally have a preference because I find it easier to draw one loop at a time. So if I back up to negative pi over 4, then when I start drawing on a grid, which I need to grab my grid. 1 second. Don't look, don't look. I was kind of joking, but not. Got B. Good. I don't want you to see the graph. Ah. Okay, can't see it yet. Paste. Really? You pasted way over there. Now where'd it go? Ah! This isn't working out for me, is it? Okay. Oh, there it is. There it is. I'm going to shrink it a little bit and move it in. Okay. So as I travel from negative pi over 4, negative pi over 4 to positive pi over 4, I start at 0, and I'm going to call this 1, radius 1 right there. I spiral out to 1, and then I spiral back in to 0. This is called a rose curve, and that is one petal of the rose curve. There, 1 is just this piece right here. As I continue along the graph, so I just graphed this much. Now it's going to go negative. So I have a negative radius as I travel from pi over 4 to 3 pi over 4, where it peaks at pi over 2, but it peaks with a negative radius. So pi over 4 to 3 pi over 4, but with a negative angle. So where is the negative side of that line turning? It's actually turning on the other side. So it, at pi over 2, it is peaking at negative 1, and it is spiraling out and back in. Then, from 3 pi over 4 to 5 pi over 4, another loop takes place, but this time it's a positive radius. And it reaches r equals positive 1 at pi. Whee! And then, let's see, what color? Okay, do that color. Negative radius from 5 pi over 4 to 7 pi over 4. So that means that while my angle is turning through here, it is graphing through here. Wow, this is called sharing at its best, isn't it? So basically, these angle ranges decided, you want to be best friends? I'll give you my rose petal. Oh, yes, I'll be your best friend. I'll give you my rose petal. And we each get one. And then the other ones are just like, no, that's mine. And they keep it, but everybody has a petal. Now I want to bring up another graph. This time I'm going to do cosine 3 theta. I'm going to do a quick draw. Whee! Over here we have 2 pi divided by 3. Cut it in half. Cut it in fourth. And then what is pi over 6 times 3? And then this gets us going. And I want to make sure to, because I really like going about it that way. Let me grab my grid. And let's see how this one plays. All right. Negative pi over 6 is here. Positive pi over 6 is here. And I want to keep drawing these out. So pi over 6 will then go to pi over 2. I'm looking at what are these intercepts. Do you see the pattern of how much angle a loop takes up? A loop takes up a pi over 3 amount, and halfway through it does its peak. And I'm going to put in angles, all the angle. I'm cutting it up with what would be showing up as the x-intercepts of that. Now, how many equal slices does this create? 6. If I go back to this one, how many equal slices did that create? So, do you see the pattern of slices? Double that number that theta is multiplying to, and that's how many equal slices you create. But here's another thing, and watch. From negative pi over 6 to positive pi over 6, and I'm going to call this r equals 1. I get a positive radius making a loop going, yay, I love my rose petal. I'm not sharing it with anybody. Then we hit a negative radius while we go from pi over 6 to pi over 2. So I'm going to actually graph opposite that. And it's going to go, wee. I like my, I'm going to give you my leaf. Do you like my leaf? Oh, no, not leaf. I sometimes call it leaves because, you know, leaves. Petal is officially called a petal. That is the math word. So I give you my rose petal. And it's like, oh, thank you. I love rose petals. Then pi over 2 to 7 pi over 6 gives us our next loop, positive radius. So it's now graphing, where am I at? Or am I, hold on one second. I almost lost the thought of where I was located. I just have, don't give me the 10-minute warning. It's not 7 pi over 6. I'm getting ahead of myself. 5 pi over 6. Positive radius. Yay! Then, after 5 pi over 6, it goes negative until you hit 7 pi over 6. Look at where it's graphing. It's like, oh my goodness, I like you. I'm going to give you my rose curve. And it says, hey, thanks. I like rose curves. I don't share, though. Then we're going to hit 7 pi over 6 to 3 pi over 2. And that goes back to being positive. And it looks over at the pi over 6 to pi over 2 and says, I appreciate the rose petal you gave me. And, oh, yeah, I like mine too. And then it goes back to a negative radius. And I think you see what happens. Odds don't share. Odds don't swap. Evens either say, I like my rose petal and I'm not sharing, or it swaps with the one across from it. But when you have an even number, that means over a pi amount of a turn, you have an even number there, if that makes sense what I'm trying to say. But take a good look as to what the difference is between the even versus the odd number in the going back and forth. When you make a pi amount of a turn and you go back and forth, do you see that you don't end up doing the full share swap? So what you want to be aware of is with these rose curves, if it's an even number, then every section gets a petal. If it's an odd number, every other section gets a petal. And the number of sections you divide it up into is double whatever that number is. So I thought that was important to at least share with you. And I need to throw some problems your way for homework, I think. I'm sorry. Because we are so low on time. Now, another thing you need to be aware of is if you want to find slope when you're dealing with a polar graph, it's still dy dx. You can manage it in a parametric way if you take the formula for x and the formula for y and you use those formulas, because you're going to be given an r equals f of theta function and asked for slope at particular angles. So what you're going to have to do is use the fact that x is equal to r, which is this function, times the cosine of theta, and the fact that x is equal to r, this function, times the sine of theta. Then you're going to find dy d theta and dx d theta. And yes, that's product rule and product rule. But if you understand how to write them in a parametric manner through these formulas, you can do the slope no problem. You may not want to, but you can. And that is something you're expected to know on the AP test. And it is right now 12. Oh, wait, we've got 5 minutes. What? Okay, so maybe I can show you this. With any of these functions here, these are just asking you to find slope at a particular theta. So some of these are easier, some are harder. Let's do this one, number 61. What I like to do is write y on top and x on the bottom so I don't accidentally do dx over dy. I know that y is equal to r times sine theta. I know that x is r times cosine theta, and now I'm going to put the r in. And now I am going to find dy dx. Sometimes you can nicely simplify what you have, and it doesn't always simplify. It doesn't simplify here. So for dy, you are going to product rule this pair. Keep one, derivative of the other, plus swap. Derivative of the cosine of 2 theta is negative sine, plug baby and multiply by derivative of baby, multiplied by, keep the second one as sine theta. Denominator. For x, I'm going to keep the cosine 2 theta and then multiply by the derivative of cosine theta plus and then swap the derivative situation. I already know the derivative of cosine 2 theta, so let's use that to the advantage. And then keep the cosine theta as we are using the product rule. You now have a formula in terms of theta for slope. At that point, you can take pi over 4, plug it into every theta, and come up with a number. Is it time consuming? Yes. Pi over 4 times 2. Nope. No calculator. Now, save yourself some time. Is anybody 0? I've got a pi over 2. Who is 0 at pi over 2? Zero times, I don't care. 0 times, I don't care. Less to focus on. Just this now. Sine of pi over 2 is 1. So negative 2 times 1, negative 2 times 1. And then what is pi over 4? Who cares which one's sine and cosine? And so when I multiply that together, I end up with negative root 2 for my numerator. Oh my goodness. Negative root 2 for my denominator. Look at that, the slope is 1. Huh. Now, let's remember what graph we just used. Cosine 2 theta at pi over 4. Let's go look real quick. I'm going to go to their graph. Here we go. Ah, don't do that to me. What's happening at pi over 4? So the graph at 0 is here. And then as I go from 0 to pi over 4, and then after pi over 4, I come through here. So I'm just making this big curve right here. Do you see that the slope, as it goes through the origin, makes sense that that slope is 1 right there? That's what that just found. And in fact, let me just show this because it's just so beautiful. If I start at 0, I go loop-de-loop, smooth and steady, smooth and steady. Whoops. And it's just so beautiful. Oh, and there's the bell. Tomorrow, all we do is area.